Good day. So today we're going to look at the ordination, then also other analysis. So the aim of ordination is just to summarize the sampling data into simpler, less space-consuming fashion than the table method. Then the polar ordination. Then the first step is just to create a matrix of community coefficient of values between all possible pairs of stands. So gradient analysis, therefore, is just the analysis of the vegetation along the gradient, that is along the slope. So by looking at species richness and also species distribution along the slope. So today's gradient analysis will be conducted on the mountainous slope. So by observing with detail on how plant species is distributed with respect to different altitude. So the mountain plant species are distributed along altitudinal gradients, meaning that species richness will decline or incline with altitude. So this is because plant species composition varies with changes in soil characteristics and also the topographic position, that is from the bottom to the top. So the altitude and also the elevation of the land has a great influence on our plant's growth and also development. So at lower altitude, the climate becomes too harsh and permits certain plant species to grow. That is why at the highest point of the mountain there is less or no vegetation at all. So those conditions include the environmental factors that causes unevenness in species richness and also species distribution on a mountain slope. So those factors include what we call aspect, temperature, soil type, light, moisture, availability of nutrients, and also what we call nutrient runoff. So we're going to explain this separately. So this is how we view a mountainous slope. As you can see from the top there, it's barren, it's said to be barren rocks. As we go down, you start seeing the pioneer species. Now the mosses and lichens, and then we have the cushion plants, we start having grasses. As you go down, we start having dense trees or forests. So this is how normally the distribution of plant species would be along the gradient. So we're going to look at the first factor, which is the aspect. So it just refers to the horizontal direction to which a mountain slope faces. So aspect has a strong influence on the temperature. So this is because in most cases, the south-facing slope will be warmer than the sheltered north-facing slope. And we expect that the south-facing slope should have more species than the north-facing slope because it receives less sunlight. So this can have a major effect on the altitudinal and also the distribution of vegetation that requires large quantity of moisture. So the south-facing slope is said to be much drier because it receives more direct sunlight, and the vegetation there should be more of drought tolerant, and the north-facing slope is said to be a bit warmer. So when it comes to temperature, the bottom of the mountain, the temperature is warmer, thus enabling more species to develop and grow. But with the altitude, as you know, the higher you go, the colder it becomes, which means we're also going to have limited vegetation as we go up. The moisture, so water holding capacity is very important. So too little water or too much can damage plants. That is, there is less water, the tissue of the plants will dry up. And if the soil becomes waterlogged, oxygen availability will be less because of poor aeration. Then we have light. So the light refers to the intensity and also the concentration of sunlight. So the more sunlight a plant receives, the better the capacity it has to produce plant food through photosynthesis, as you will see in your second semester classes when we talk more about productivity. So with that said, we also have a problem with the vegetation mapping. So that is, vegetation types are generally described in paragraphs rather than by tables, numbers, or graphs, and the results reflected the bias of what a mapper regards as important differences. So mapping generally begins by examining aerial photographs. So photographs such as these, the ones which you would observe from when you are standing in an higher elevation. So from the photographs, the investigator then tries to distinguish as many different communities of vegetation types as possible, outlining the boundaries of each on the acetate sheet placed on top of prints. So the next step is to go back to the field now and examine the representative of each mapped type in order to identify the dominance and check the reliability of the interpretation of the photographs, which we call the ground truthing. So it also has some limitations, so which are imposed by the scale and also the objectives. So the level of detail that can be shown on a map is limited to a scale. Many of the boundary lines drawn on the vegetation maps do not exist in nature. The community of vegetation type can typically change gradually into adjacent one through broad range ecotone. So the line on the map may represent a midpoint of an ecotone instead of a boundary line. So if the ecotone is usually large, or several types coexist in some complex mosaic, the ecotone or mosaic may be mapped as a separate unit on its own. So those are the limitations we have with the vegetation mapping. With that being said, we find that there are also advantages of using the aerial photography on vegetation studies, because it provides a current pictorial view of the ground that no map can equal. It is more readily obtained. The photographs may be in the hands of the user within few hours after it is taken. A map can take a month to prepare. It can provide a day-to-day comparison of selected areas. It provides a permanent and also objective record of day-to-day changes. But it also has some disadvantages. The advantages are that the ground features are difficult to identify or interpret. The position and location and also the scales are only approximate, so we do not have actual numbers. So we need more training to interpret the maps. It is difficult to identify submerged vegetation because we're only taking photographs, and then we do not go deep into the water because we're taking aerial photographs. And then we're going to look at the remote sensing. So remote sensing literally means to observe and measure an object without touching it. So that's why we say remote sensing, the same way as you would do with a TV remote. So in the environmental sciences, it refers to the use of sensors detecting electromagnetic radiation reflected or emitted from vegetation and soil surfaces. So because satellite sensors acquire data in infrared and also microwave spectral bands, in addition to visible bands, they provide a new source of information for research. So since data are recorded as numerical brightness values for each band, statistical analysis and data transformation are possible. So they are made for visual presentations by assigning shades of gray to digital values. It can be used to determine the spatial distribution of vegetation types, patterns associated with habitat boundaries, and also land uses. So we've got types of remote sensing, two types actually. So we have the passive sensing, which detect natural radiation that is emitted or reflected by an objective or surrounding area being observed. So reflected light is most active passive common source of radiation measured by passive sensors. Example of the remote sensors include film photograph, eye, and radiometer. So these ones are passive sensors. We have active remote sensing. So on the other hand, it emits energy in order to scan objects or areas whereupon a sensor then detects and measures radiation that is reflected or backscattered from the target. So a radar is an example of an active remote sensing where the time delay between emission and return is measured, establishing the location, height, speed, and also direction of the object. So we also have principles of remote sensing. So remote sensing is actually done from satellite or airplanes or on the ground. So remote sensing uses instruments that houses sensors to view spectral, spatial, and radiometric relationships, observable objects and materials at a distance. In much of the remote sensing, the process involves the interaction between incident radiation and also the target of interest. This is amplified by the use of imaging system, where the following 7 elements are involved. So the 7 elements involved in remote sensing are these ones, A up to G. So A there is the energy source. So this is the first requirement for remote sensing. So for remote sensing to take place, we must have an energy source which provide electromagnetic energy to the targets of interest. And then we have B and the atmosphere, radiation and the atmosphere. As you can see there, we are in space. The atmosphere, as the energy travels from its source, which is A there, to the target, it will come into contact with the atmosphere and then interact with it and then pass through it. So the interaction may take place a second time as the energy travels from the target to the sensor. And then we have C, and C there, that is the interaction with the target. So once the energy makes its way to the target through the atmosphere, it interacts with the target depending on the properties of the target and the radiation. Then from there we go to D. where the recording takes place, the recording of energy by sensors. So after the energy has been emitted from the target, we require a sensor to record and also collect the electromagnetic radiation. So that occurs there on our satellites. And then we have E, as you can see E there. So the transmission, reception, and also processing occurs at E. So the energy recorded by the sensors has to be transmitted, and often in electronic form, to receiving and processing stations where the data is processed. From there it should go to F, where it must be interpreted and analyzed. So the processed image is interpreted visually and or digitally or electronically to extract information about the target which was illuminated. From there, the last place is G, the application, which is the final element of the remote sensing. So it's achieved when we apply the information we have been able to extract from the imagery about the target in order to better understand it and reveal some new information or assist in solving particular problems. So the types of remote sensing systems. So we have got visual remote sensing systems. The human visual system is an example of a remote sensing system in general sense. So the sensors in this example are the two types of photosensitive cells, known as the cones and the rods at the retina of our eyes. So the cones are responsible for color vision. There are three types of cones which are being sensitive to one or of the red, green, and the blue region of the visible spectrum. Thus, it is not coincidental that the modern computer displays monitors make use of the same three primary colors to generate a multitude of colors for displaying color images. The cones are insensitive under low light illumination condition when their job are taken over by the rods. So the rods are sensitive only to the total light intensity.